UFS webinar series. Today, our webinar is going to be about the GEFS version 12 Reanalysis and Reforecast, presented by Tom Hamill. Robert Webb will be introducing Tom to the audience. Go ahead, Robert.
So I'm pleased and proud to introduce Tom as the speaker today. Tom Hamill has had a rather impressive career going through, starting as an undergraduate at Cornell, going to Penn State after that, and then I believe he took some time off and spent it in Nebraska as a U.S. Air Force officer in charge, and then went back to grad school at Cornell University. He's been basically in Boulder since finishing his PhD as a postdoc at NCAR, and then coming and working for Ceres and the Climate Diagnostics Center, and then eventually became a meteorologist now in the physical sciences laboratory. Tom has been at the forefront in terms of how do we use and develop reforecasts and reanalysis in improving our ability to post-process and also evaluate forecast model output. And I'm not going to go into too much more detail, but let Tom go into his talk starting now. So Tom, it's all yours.
Thank you, Robin. Oh goodness, let's see here. I might have to fiddle with.
Yeah, Tom, you are the presenter. The stage is all yours now.
Okay, can y'all hear me? I'm hopeful that that you're able to see my screen shortly. If not, the fallback position, I guess, window. Can you see me yet? It doesn't appear that you can. I mean, see my screen.
We see you, but not your screen.
I can see you, but not screen.
Okay, then let's, rather than watch us fiddle around, we'll have the slides displayed by the folks organizing the call, and I'll just have them flip through them for me, okay?
Okay, can you all see my screen?
Not yet.
Nope. We don't see you yet, but we just still see Tom Hamill.
Okay, sharing. Give me a second. I'm clicking share screen, but it's not sharing.
Isn't this the way things go in the age of COVID here?
So Tom, do you have to release as being the presenter?
Well,
oh, that could be it.
I'll go back and I'll see what we can do.
I could lengthen my introduction.
How about I go ahead with sort of, there we go.
Yeah, there you go. I think that's what would happen.
Okay, so a few weeks ago, maybe a month or two ago, my colleague Vijay Talapragada at the Environmental Modeling Center provided you with an overview of version 12 of the GEFS, the Global Ensemble Forecast System. And his review showed, the many very positive improvements that have been accumulated over several years of recent development. Now, this is going to be a talk about specifically about the reanalyses and reforecasts for this system. For the first time, we're accompanying the real-time implementation with a pre-computed set of reanalyses for the reforecast initialization and those retrospective forecasts that span a 20-year period. I'd like to acknowledge many colleagues, both within my own laboratory and colleagues at the Environmental Modeling Center, and really for lack of space, I've omitted others at the Office of Water Prediction and the Climate Prediction Center. I swoop in, pardon me. I swoop in and sort of act like I'm in charge here, but really the bulk of the work has been done by the people listed in black. Okay, let's move on. Second slide. So here's an outline of what I intend to talk about here. A review quickly of what VJ presented in more depth on the major changes with the next version of the GEFS. A review of why we choose to do reforecasts and why we're choosing to initialize those with a new reanalysis this time. And then I'll go into the meat of the talk, characteristics of this reanalysis relative to the previous mainstay, the climate forecast system reanalysis, and look at this in terms of fit to observations and skill of forecasts from the two reanalyses. And I'll also provide a little bit of a look toward the future in GEFS version 13 and beyond. Next slide, please. Okay, a quick review of what VJ presented. So as I think you know, there is a new dynamical core. We've changed from a spectral dynamical core to the FV3 one developed at the Geophysical Fluid Dynamics Lab. And in our GEFS version 12, this is applied at a C384, that's sort of 384 by 384 grid points across a cube. And that works out to roughly a 25-kilometer grid spacing. This dynamical core is less diffusive, and that means there's more small-scale variability. And I think that's particularly helpful for improving important things like precipitation forecasts. The real-time forecasts 4 times a day, there are 31 members that go out to 16 days lead time, and then once a day, 31 members in the real-time forecast to 35 days. Now, while we have colleagues that are working to break new ground on stochastic physics, we basically, in this version, have followed the best practices that have been developed internationally at locations like the European Center. So we have stochastically perturbed physical tendencies and kinetic energy backscatter. And these two, as well as a couple other aspects, provide much more realistic estimates of uncertainty in this system relative to version 11 or version 10. Now, we did not have the time to incorporate a fully interactive ocean. So what's being done is a transplantation of the evolution of anomalies from the older climate forecast system to get some change apart from the change in climatology into this system, but we expect newer versions will be fully coupled to the ocean. And as VJ showed, the results are much improved forecasts. Now, the concentration on this talk is describing the reanalysis in particular and a little bit about the reforecast. I am going to also concentrate, even though our reforecasts go back prior to 99, I'm going to only concentrate on 2000, the current, which is the period where we did the reanalysis. And we chose starting in 2000 because that was the advent of the AMSU-A era, the modern sort of satellite microwave radiances. And in the previous generation CFS reanalysis, they found that there was a big discontinuity before versus after that period. And it's likely we would have suffered that same discontinuity here, sort of an unavoidable consequence of a major change in the observing system. Next slide, please. So for the first time, we're sort of recognizing the reanalysis and reforecast as a vital part of the actual end-to-end operations. Now, there's of course data assimilation and that precedes the running of an Ensemble prediction system. But the idea is that your real-time Ensemble predictions are going to be post-processed using past reforecast ensembles and observations and analyses. And then a lot of the decisions that customers of NOAA will be making will largely be based upon post-processed guidance. And this includes products from the Climate Prediction Center, the Office of Water Prediction, and in the future, the National Blend of Models guidance will also reflect this. Next slide. Now, why are reforecasts particularly important? When we consider longer lead forecasts or forecasts of more high impact events, and here I'm looking at about an inch of rainfall and probabilistic skills there. Let's compare the top two panels here, panel A and panel C. In version 10 of the GEFS, the raw skill of a one-day forecast is about 0.1 in the wintertime. And it's about that's the skill of about a 4-day forecast with the reforecast based post-processing. Apologies if you hear a dog outside, that's my neighbor's dog. Adds a little local color, I guess. So 3 days gain, which is kind of roughly equivalent to almost 3 decades of prediction system development here from the use of the longer training data set afforded by a multi-decadal reforecast. Next slide, please. With the post-processing, the forecasts also go from the raw forecasts on the right-hand side being quite unreliable. So when we forecast an event happening 80% of the time, it's actually happening more like 40% of the time. But you can see with that post-processing, we've made the forecasts reliable. You can really count on the probabilities quite realistically there. And in that way also, the burden upon a human forecaster to massage the product before sending it out is relieved. And those human forecasters can really concentrate on the high impact events and holding the hands of major customers making major decisions from the data. Next slide, please. As we move to more and more challenging applications, and here I'm showing you precipitation typing, we especially end up benefiting from the long training data sets here. So this was an example that we did that composited data from across the United States to try to develop methods for generating precipitation typing based upon profiles of I think it was wet bulb temperature here. I might be wrong. In any case, I think you can see that the differences are there, but that compositing across the United States was a consequence of us not really having saved out full vertical resolution data in the previous reforecast. We will have that now, and we'll have that across a 20-year time period. And we expect to, for example, be able to make more localized training of the data so that precipitation typing in the Front Range here in Colorado would be different than it would be in North Carolina, as you might expect, with potentially different systematic errors in the systems at those two locations. Next slide. So this set of new reforecasts is preceded by a new set of reanalyses, and these are very computationally expensive to generate. And so a question you might be having is it really worthwhile? Well, the climate forecast system changed from using their own reanalysis procedure to using the operational analysis. And when they did so, this is an example of some pretty large systematic changes in the character of the thermodynamics that can occur. Let's focus on these yellowish lines here. So this is a distribution of CAPE shown in the area in the inset diagram, basically the Midwestern United States in sort of, the tornado season. And that distribution of CAPE in the old reanalysis prior to 2011, and then afterwards, when they switched to the CFS being based upon the real-time analysis, that distribution of CAPE shifted dramatically. Now, the blue lines show you that a one-day forecast, even though the model exerts a strong influence on the climatology and the two are becoming closer together, there's still a quite dramatic difference in 24-hour forecast CAPE distributions across this area. They are more muted out once you get out to 5 days a week, but they're still there to some slight extent. So the thought was, if we went back and we did these multi-decadal reforecasts off the old CFS reanalysis, we would see more of this sort of problem. The analysis continues to evolve here, and reinitializing the old forecasts off a system that didn't reflect the modern day assimilation technology and the modern forecast model was going to cause statistical inconsistencies between the reforecasts and the real-time forecasts. And that's what we aim for with statistical post-processing. Next slide, please. Now, if you go and you choose to use a different reanalysis, such as NASA's MERA reanalysis, or perhaps the ERA5, the current one from the European Center, those are not so much designed with reforecast initialization in mind. They're not designed to optimize for consistency with the real-time system. They're a little more concerned about the absolute accuracy of the reanalysis. Here, our focus is on that consistency. So even at the expense of perhaps some more biased near surface temperature analyses, if those biases are consistent with the bias in the operational system, that leads to a statistical consistency in the resulting reforecasts and better statistical post-processing. So that's our goal with this reanalysis, and I think that's worth keeping in mind. If you're out there looking for a reanalysis for model verification or climate variability, I think you might be better off choosing a different one. But if you're doing experiments, let's say under the umbrella of the new EPIC program, and you have an experimental version of the global forecast system, and you want to run an old case like a Hurricane Katrina, then our reanalysis initial conditions are the ones that you would choose because they have that consistency with the operational system. Now, as we continue to knock down the systematic errors and build in the coupling of land, atmosphere, and ocean atmosphere in the data assimilation system, I expect that we will have an analysis within NOAA, a reanalysis within NOAA that is more capable of serving the multiple needs. But for now, this is where we are. Next slide, please. Okay, a brief tour of the major differences. The reanalyses have a different period of record. The one I'll be talking about today is really 2000 through current, again, that AMSU-A microwave radiance period and forward. We have a new dynamical core, a new microphysical parameterizations, and then some other changes to the parameterizations. Another major change is going from the older 3D VAR to a hybrid 4DN VAR system in the current system. There was not an ensemble in the old CFS reanalysis, and the background error covariances are provided by an 80-member ensemble Kalman filter at a reduced resolution in this reanalysis. In the cycled DA, we have stochastic physics that have been modernized and some other changes that you can see as in the columns that I won't continue to read on. Next slide. The vertical number of levels are now 64 levels, and depending upon how you look at it, in a logarithmic scaling on the left-hand side, linear on the right-hand side, it sort of appears whether kind of coarse vertical resolution in the stratosphere or pretty decent resolution. And the stratosphere we think is, particularly important as you get out to longer lead times for phenomena that may have some predictability on timescales of many weeks, such as the impact subsequent to sudden stratospheric warmings. So, it's an ongoing question as to whether we really have truly sort of optimized this to provide a good stratospheric analysis. I'll show you down the road that we have a fairly realistic QBO at least. Next slide. Okay, so what are the differences not between the current reanalysis and the old CFSR, but our reanalysis in the operational system, and what known bugs do we have? First of all, we could not afford to do the operational, the reanalysis at the same resolution of the operations. So the control analysis is at double the grid spacing. We also chose not to use the same sea surface temperature analysis procedure known as NSST that's used in real time, because we found that in the more data sparse period of the reanalysis, that really wasn't a trustworthy thing to do. So we defaulted to using the older OI analyses that had already been produced. One problem that we made was the snow initialization was updated to the snow analyses only once per day. We attempted to go back and correct that through a procedure that NASA has developed called replay. Rather than go through what that does, I'll just provide you with that hyperlink, and you can go look at or Google this if you wish to get a sense of how you use the analysis increments in a way that allows you to sort of bring back some of the lost detail. We also had a few observation problems, such as the VAD winds that were the QC was not finding bird migration problems, and we turned that off when they were discovered. And frankly, we do expect that, as more people comb through the reanalysis, they'll likely find some more issues. And, that's an inevitable consequence of a very complicated system where there are roughly, 100 different flavors of observations that are being assimilated, and a limited, number of staffing hours to look at all the possible issues there. Next slide, please. Okay, in the stuff to come here, we'll be looking at the quality of the reanalysis in a couple different ways. First of all, as we cycle the data assimilation, we have short-term background forecasts and then the newly available observations before they're assimilated, and how well the background forecasts fit those new observations is one metric of quality that we can use to determine whether or not we have improved the analysis. We can also run what we call scout runs, a deterministic version of the FV3 GFS from older reanalysis initial conditions and from our newer reanalysis, and then verify them against an independent source. And I'll show you some of that. Okay, let's go on. Next slide. So here is one of the problems that we did find. So you'll notice, for example, in roughly mid-2006, there's a jump in dry global pressure. What was responsible for that? This was actually calculated with 6-hour forecasts, but we expect the same to be reflected in the analyses. And let's jump to the next slide. So this was at the time of when the GPS radio occultations, or GPS ROs, which are a powerful, unbiased measurement of effectively the thermodynamics, became more widely available. And so starting around the 13th of July, those ramped up dramatically in the number of observations that were available. And next slide. They provided an independent look at the temperatures. And in doing so, they became a source of information for what we call anchoring the satellite radiances, which previous to that point didn't have effective information in many situations for making statistical corrections when you have a discrepancy between the model forecast and the observations. There's a question of, is it the observations, is it an observation bias, or is it a model bias? And it wasn't until these AMSU-A observations came online that we found out that the radiances did have some bias. And then subsequent to July 2006, there was a major adjustment in the satellite radiances and an overall adjustment to the temperatures in the reanalysis. And the vertically integrated temperature is related to pressure, and in such created a change in the pressure analyses. So that was the source of that one. There's another one that we're still exploring a couple of years later. Next slide, please. Okay, let's take a quick look here and just note that the water cycle is not closed in this reanalysis. We hope to see that at least over a couple cycles or weeks or months, precipitation matches the evaporation. There shouldn't be, except at, really a decadal timescale with global warming, a change in the moisture content in the atmosphere. And so we do see that there is not this balance that is more carefully balanced in other reanalyses such as NASA's MERA-2. So this is just, what the system gives, and it's worth being aware of that if you're trying to use this reanalysis for like water cycle type relationships. Next slide. To make the reanalyses computationally tractable, what we did was to divide them up into 5 different streams with overlaps. Now, we actually have a stream that started not in 2004, as might be implied in that upper graph, but in 2003. We started that stream at the beginning of 2003, but we throw out the first year as a spin-up period. And so then only after that first year do we change from using the first stream to that second stream of data here. Now, you could imagine that there could be problems, though, with very slowly changing quantities like the soil moisture here. And do we have a problem? Well, as you look at that time series in 3 different regions here, and these regions were chosen to be ones that are where there's a strong land atmosphere coupling strength. Well, in terms of the box mean average, that's what the time series are representing. And you can see that there doesn't appear to be a discontinuity there. And then looking at individual grid points within the box and taking the last day, for example, at the end of the black time series and the first day at the end of the blue time series, and the statistical relationships are shown on the scatter plots there. You can see a very, very strong consistency between the two. This is for the second level down soil moisture. And this is one diagnostic that makes us think that we probably do not have major problems as a consequence of dividing the reanalysis up into these multiple streams, which was a practical necessity for getting this done on supercomputers in a limited amount of time. Next slide. Here is a look at the Quasi-Biennial Oscillation. This figure was produced by my colleague, Zach Lawrence, so thanks to him for that. And I guess the main thing for you to note is that there's no smoking gun sort of problems here. We do see a QBO in this reanalysis, and there does appear to be a decent fit to the observations. For example, this one particular station in Singapore. Next slide, please. Okay, now we're going to go on and look at several slides that have similar sort of ways of plotting the data. And what I'm showing you are in the dots, weekly averages of the fit of the background forecast, the short-term forecast, to conventional observations in this case. And up top is root mean square error, down below is bias. And there was an annual cycle to this. And so I also fit some regression lines, and those regression lines include an annual cycle there. So the reanalysis is in red, the modern reanalysis is in red, and the older CFSR is in blue. And in this case, the low level temperatures show a slight improvement, and no concerns about biases shown in the lower hand plot. Now the biases didn't seem to have that same sort of annual cycle, so those were the lines were fit with a Gaussian kernel smoother there. Next slide. Now here's something a little more interesting. Let's look at a higher level. This is 300 to 400 millibars. And during this period, up to roughly 2006, 2007, the CFSR might have been slightly better with the fit to the conventional observations. And then it appears that the GEFS reanalysis was better. If you look at the biases in the lower plot, you see a dramatic change in the biases there. And recall from a couple slides previously that this was a time when the GPS radio occultations became widely available. So those GPS ROs, became an effective bias correction for other bits of instrumentation and helped really knock down the forecast bias at that point, and also improve the root mean square errors at this level of roughly 300 to 400 millibars. Now this is an interesting level, 300 to 400 millibars, and we'll return to considering some issues at that level in future slides. Next slide, please. Okay, so here's now a look, instead of a conventional observations, the NOAA 15 AMSU-A channel 8, which peaks roughly, 150 millibars or 180 millibars. And here you see a pretty dramatic improvement in the root mean square error of the background forecast fit to those radiances for the new reanalysis and relatively comparable biases. Next slide. Now, this might lead you to think that we have a major problem with our reanalysis. When we look at channel 3, and channel 3 is a surface peaking channel, our reanalysis appears to be much, much worse. But there is a major change. And that major change is our reanalysis, excuse me, assimilates cloudy radiances as well as those after cloud clearing. So there's much more data that's assimilated, and as a consequence, the additional data, the fit in those cloudy regions is substantially worse, and that's what makes it look worse here. But we do not think that this is actually a sign of a major problem in the reanalysis. Next slide. And now I'll look at channel 7 here, which was returning to this area around 300 millibars, where we had seen some issues of bias previously. And here, the AMSU-A channel 7 background bias does appear to be a little worse. And this is despite the GPS radio occultations here. So I'm still a little bit scratching my head to try to understand that. My strong supposition would be that this is a channel that peaks in, the tropical upper troposphere, where we seem to have the worst biases actually. And it's possible that the new microphysical parameterization has made a major change in cloud cover in that region, and that's had a substantial impact on the bias. Let's go to the next slide, please. Again, I will return to that problematic 300 millibar level in a moment here. But let me take a look now at a comparison that's looking at the evaluation in a slightly different way. Is our reanalysis systematically different than the real-time analysis, which will be done with a higher resolution version of the system and have a couple other changes noted in the previous slides? So first of all, let's focus on the oceans here. Recall we used the OI analysis procedure versus the NSST. And in the tropics, it does not appear like there's any real systematic differences. And that's a good thing to see, because I think the tropical oceans are more interconnected with the deep tropical atmosphere. And the more northern extratropics and the southern extratropics affect sort of a thinner layer of the atmosphere. So while you do see differences in the North Pacific, the North Atlantic, and the Southern Ocean, I think that these are potentially less problematic. Now, we do seem to have skin temperature differences, such as in the Himalayan Plateau, Greenland, Antarctica. Skin temperature, I did not provide an analysis of the 2-meter temperatures. I would expect them to be more muted. Skin temperature, really feeling the effects of the ground surface is often much more finicky, much more sensitive here. And so despite the fact that we see in these regions 1, 2C, sometimes even 4C differences, I don't think that this is like enough of a red flag. And I would note the previous bug that I mentioned, which is that we made the mistake of updating the snow analysis once daily as opposed to 4 times daily. We attempted to ameliorate this with an update to a replay procedure, but I think that may be partly responsible, the lack of a 4 times daily snow refresh. Another possibility for the land differences is that while we were producing the reanalysis, the global land data assimilation system was in flux, and that's used in the operational analysis procedure, but it was not available to us in the reanalysis. So we don't have a correction of the land state using GLDAS in our own reanalysis. We recycle the background forecasts provided in the hybrid 40 NVAR procedure. Next slide. Okay, pardon me for hopping around a bunch. This is now returning to the question of that pesky 300 millibar bias here. So let's sort of block mentally out the bottom 2 rows of panels and focus on the top ones here. And in particular, we have a set of panels that are showing you the root mean square error differences in deterministic forecasts for 3 different regions. That's the 3 panels. And the differences are between the same forecast model, a deterministic run of the FV3 GFS, one initialized from GEFS V12, another from CFSR. Where you have blue regions, that's a sign that those forecasts are better in the GEFS V12 initialization. Where they're red, they're better in the CFS initialization. And you can see that it appears using ERA interim as the verifying analysis that there's an initial problem there. The short lead forecasts from our system appear to have significant bias. That diminishes with increasing lead time, but it's a concern. In terms of looking down now at the lower panels, here you see the middle set of the middle row is the actual bias and how that evolves with time. And you can see those biases, regardless of whether they're initialized off the CFS reanalysis or the GEFS V12, grow with time. And that's a hint that, this is probably traces back to a deficiency in the forecast model itself. The forecast model is doing something to cause near tropopause temperature biases there, especially in the tropics, but evident in both hemispheres here. And so that's why we hypothesize that the change in microphysics is one area that we could be looking at. And I would hope that this would be an issue that the UFS physics team would be looking at as they proceed. Next slide. Okay, just to show you also before versus after the GPS ROs were assimilated, things were somewhat better on the right-hand side after GPS RO versus on the left-hand side before GPS RO. So that did have somewhat of an impact on diminishing those biases. Next slide, please. So now we're turning our attention to a different forecast diagnostic. And this is what are commonly known as die-off curves of anomaly correlation. In this case, I'm just taking the U wind component at different vertical levels, that's the columns here, and northern hemisphere in the rows, top tropics middle, southern hemisphere bottom. And the different curves that you see, 5 different curves, are the different streams. So one stream from 2000 through to 2003, another for 2004 to 2007, and so forth here. And in this way, you can see if there's consistency across time in the improvement. The dashed red are the die-off curves from our reanalysis, and then the cyan colored curves are from the old CFS initialized forecasts. And especially in the tropics, you see a notable improvement. It's less prominent in the northern hemisphere, but it's still there. It's very prominent in the tropics and somewhat prominent in the southern hemisphere here. Next slide. Okay, this is just to acknowledge that we do have more work to do. So one thing I would like to look at, for example, is we've had to use a lower resolution version of the data assimilation to generate this multi-decadal reanalysis. And will that result in a substantial degradation in the quality of the forecasts? Well, we can look at this by comparing the operational, the pre-operational analyses that were available for roughly 2 years, the last 2 years, versus forecasts initialized from our reanalysis, I should say there, rather than reforecast. And regrettably, we don't have this available yet. Next slide, please. Okay, turning attention to the data, because I think that a lot of the callers here to this webinar are interested in accessing this data. And here's what we plan to do. We plan to store the data in 2 places where there will be public access. Under NOAA's Big Data Project, roughly 200 fields. So this includes many, many fields near the surface, and then lots of mandatory pressure level data comprising a total of about 200 different fields. Those will be stored at high resolution during the first lead times of the forecast, and then at reduced resolution at longer lead times. But we'll be storing that data to the Amazon Web Services cloud, and then we will be making that available on NOAA-owned disk in probably still more than a month out. A disk cluster that will be attached to what we call the RZDM computer, which has connectivity with the operational supercomputer. And we'll make this available by FTP, web interface. I suppose it's possible that there may be OpenDAP. I'm not sure about that. So our intent is to seed the broader community. And my hope, frankly, is that, we do, to be honest, sort of a rather basic set of statistical post-processing that I think gets us a substantial plus up in value in what we do. But I sure hope that we spur a broader community to develop advanced machine learning techniques with this data and really push the frontiers of statistical post-processing. And by making the data readily available to the broader community, it becomes just easier for the community to do this. Next slide. Okay, a talk about the future here. As I mentioned in the introductory material, our GEFS version 12 is uncoupled. We have some quasi-evolution of sea surface temperatures by a transplantation of the forecast anomalies from the climate forecast system. But as we move along, we anticipate that the next version of the system is likely to be what we call weakly coupled. And in weakly coupled, that means we're running an interactive forecast system where the ocean is forecast and the atmosphere is forecast. And those two components are talking to each other during the forecast. And in fact, this would also include, obviously, an interactive land and sea ice here. The data assimilation would still take place with separate data assimilation procedures, but that in itself, going from uncoupled to weakly coupled, we imagine is likely to change the systematic error characteristics of the near surface environment pretty substantially. And so it's probable that we would be doing another generation reanalysis. And similarly, if all goes well and the technology proves out like we expect, we would be heading towards strongly coupled in the subsequent version. Strongly coupled meaning the forecast model is coupled, but there's also a coupling inside the data assimilation. So an atmospheric observation can make an increment to the ocean state and vice versa. So because of that, we, meaning our team and our colleagues in the Climate Prediction Center and the Environmental Modeling Center, expect to continue to be busy with next generation reanalyses and reforecasts as we evolve to newer system versions. Next slide. Well, there were some lessons learned with this current reanalysis. And there's a lot of stages in producing a reanalysis, and those stages are kind of shown roughly in green along with how long it takes to do this. And then in terms of the operational implementation of the actual system, that's shown in blue here. Next slide. And a major issue that we ran into was that we had to lock down our anticipated configuration for the model to produce the reanalysis before the actual final configuration was decided. And that's not an optimal thing to do. And we're looking as we do this next time to be reevaluating and trying to use modern technologies that would allow us, and next slide, to basically do a decision on what the next generation system is going to be for the reanalysis production at the same time that our colleagues at the Environmental Modeling Center are producing the pre-production parallels here. Now, how could we do that? We think that if we could access a lot more cycles and surge, and we would do this by using cycles in the cloud on Amazon or Microsoft or Google or another cloud service provider, and use a lot of those cycles in a short period of time, then we could condense that period of producing scout runs in the actual reanalysis and reforecast production and have that greater consistency with operations. Next slide. So finishing up here, we are, changing things up here, and we're really working to have a comprehensive implementation of the upcoming Ensemble system here in version 12. That's not just an updated forecast system, but it's updated with a provision of a new reanalysis and reforecast, which will be available to the community. VJ showed previously that it provides radically improved forecasts, and we also expect a further plus up in the ultimate skill of those products through post-processing with the statistically consistent reforecasts. And we have colleagues within NOAA at the Climate Prediction Center, the Office of Weather Prediction Center, that are readying next generation products based on GEF's V12s and its reforecasts. And we have a project working with colleagues at MDL to incorporate this into the national blend of models in the future. And I certainly, again, hope that the data ends up being useful to the wider enterprise and spurs many creative applications. And with that, if there's time, I am happy to take questions.
Well then, I'll open up the session to the question and answer section. If you can type your questions in the question tab, I can read them out to Tom. No questions so far.
Okay, if anybody, also would rather address their questions to me, I'm just tom.hamill, H-A-M-I-L-L, at noaa.gov, and I'd be happy to answer, those through email.
Yeah. Just a second. Danae has a question. How do you plan on gathering analytics on the data that you provide to AWS?
How do I plan on gathering what?
Gathering analytics on the data that you provide to AWS.
I do not know myself the answer to that question. I could find out from talking with our partners in the Big Data Project about their analytics and get back to you, Danae.
A few more questions are funneling in.
Okay.
How do you decide what to work on in what order? What process or forums is enacted?
Well, if I could have you page back to where I showed the sort of the schedule of the reanalysis and what we have done in the past. Here, that's fine. Okay. This gives you a sense of how we have done this. And I really can't emphasize enough the importance of this period, what we're calling scout runs. So what we have done during the scout run period is to run a reduced resolution version of the system and find out if we have issues with data quality, if we have issues with, let's say, the anticipated parameterization suite or aspects of the data assimilation system. So there was a lot of trial and error when we ran the last set of scout runs. We would find a problem and we would go back and redo some scout runs, and we'd find another problem and go back and redo them again. So I've made this look a little bit more orderly than it actually was. There was a fair amount of confusion in the period of this scout run, and that's why we built this into the overall schedule here. And I hope that gives you some sense of the sequencing that we've done. And if it looks orderly, it was a little less orderly than you might think.
The next one is more of a comment by Jeff Craven. He says, we are excited about harnessing the GEF's V12 reforecast data in NBM.
NBM is the national blend of models, and I just very briefly touched upon that. So to give a little bit more context for those if you haven't heard that acronym, this is a passion of the Weather Service Director, Louis Ussolini, to fully leverage the national and international forecast models that are available, including those from the Canadian Center and actually the European Center. Now, we leverage the current GEFS forecasts, but we don't leverage the reforecasts for their post-processing. And eventually in the national blend, we're going to be reforecasting or leveraging those reforecasts to improve the post-processed products coming out of GEFS v12. And then they will presumably have higher weight in this multi-model post-processed ensemble system that is the national blend.
And then we have one last question by Jimmy Dudia. He asks, you had a steady decrease in RMS in some of your plots. What was that due to?
The increasing richness of the observing system is the simple answer. You know, over that period of time, we saw different international partners launch more satellite systems. So the European Space Agency data came online. Aircraft observations went from having just a few to having a tremendous number. GPS ROs ramped up and so forth.
Okay. So looks like that's a wrap for the questions. Oh wait, one more. This one's from Krishna Kumar. He says, I thought cloudy radiance assimilation would improve ops forecast for channel 3, but you said it has become worse. What does that mean?
So if we had, if I had presented there the fit of the background forecasts to the cloud cleared radiances, and I did not present that, then what I would have expected is that comparing the CFS-R fit to the observations and the GEFS v12 fit to the observations, there would have been a closer fit with GEFS v12. But what we did in the new reanalysis was to not apply that cloud clearing and assimilate only the regions that we assumed were clear of cloud, but we assimilated those cloudy radiances with the hope and expectation that that helps us provide a better analysis of the moist thermodynamics of the atmosphere. But you know, there's all sorts of issues involved in the assimilation of cloudy radiances, dealing with questionable assumptions of how well you have the emissivity estimated, for example, and that is responsible for those radiances having a much larger error characteristic. So I hope I've kind of answered that. Maybe I didn't get your question right though.
Okay. Well, we're getting close to the end of the hour. If we have no more questions, we can wrap up this session.
Thank you for your time and attention. And again, if you want to contact me by email, please do so.
Yeah. Thank you all for attending the webinar. This session is recorded and it will be made available on the UFS portal shortly. Do check it out when you get a chance. Thanks again and have a great rest of the day. Bye.
Thank you all.
Hi, everyone.
Bye, everyone.